Good morning, students. So I'm happy to meet you all. So this is Gnanasaravanan sir. So I'm been assigned to teach you electronic circuits 1 lab component. So currently we have almost completed 4 experiments. Today I'm going to teach the 5th experiment. As per sequence, it is 5th experiment. But as per the syllabus, we are skipping then and there to have a connectivity. So we have seen first experiment, which is fixed bias. Then we went on to third experiment, which is common collector amplifier. We saw fourth experiment, which is a Darlington pair amplifier. See first experiment, right? Then third experiment, common collector amplifier. Fourth experiment, Darlington amplifier. Then we came to common emitter amplifier in the last class. So today we are going to see the 5th experiment, but as per the syllabus, it is going to be the 7th experiment. So I'm skipping it then and there just to have a connectivity or to make you feel easier. So today also the experiment is going to be much relevant to the previous experiment, right? So today's experiment number is experiment number 7, but on our sequence it is 5, and our syllabus it is experiment number 7. It is frequency response of class A power amplifier. Frequency response of class A power amplifier. So this class A power amplifier and the previous experiment common emitter amplifier has much relevance. You'll know it when we go through, right? So the agenda of this experiment is to build, design and construct a class A power amplifier to measure the output voltage and to finally calculate the efficiency for various frequencies. For example, in theory, sir would have taught you different types of amplifier, and for a class A amplifier, you would have said this is the efficiency for class A amplifier, and to improve it, we'll go for transformer coupled class A amplifier, and that's how things go on. Then we'll go to class B, class AB, class C, and class D, and so on, right? So in today's experiment, this is what we are going to do it. We are going to verify whether the efficiency of class A amplifier is low. So the equipments and components required. So today we need a transistor. So the transistor I've highlighted in blue color. This is because today we are going to use a different transistor other than the previous one. So far we have used a plastic package. In this class, we'll be using a metallic package. So it is SL100. So SL100 looks like this. You can see, right? So it's a metallic package. It has 3 terminals. So this is how we are going to see any of. It's not so clear. I'll try to show it to you when we do the experiment. So we need one SL100. Then we need 2 capacitors. One is 4.7 microfarad and 1 microfarad, 2 numbers. So 1 microfarad is for coupling capacitor and 4.7 is for emitter capacitance. Then we need different resistors. So hope you have seen this. So we need 22 kilo ohms, 4.7 kilo ohms, 330 ohms, 1.2 kilo ohms. Other than this, we need regulator power supply, cathode ray oscilloscope to view, and function generator to generate the signal. So what are power amplifiers? Right, we have what is an amplifier. Amplifier is a signal booster, in one word. It is used to improve the amplitude, either voltage or the current or the both. Accordingly, it is classified as voltage amplifier, current amplifier, and both means power amplifier. So this one is going to amplify both current and the voltage. So, and especially the application of this is, sir would have told you during theory, and it's my duty also to say. So it's used in public addressing systems. PA systems and so on. If there is any orchestra or any functions or marriage, we'll use this kind of high power output power amplifiers. So that's the thing. So these power amplifiers, basically there are many types, right? So one is class A. So what I've shown here is a DC load line. So load line way of classifying it. So in the load line, class A amplifier operating point or quiescent point is in the center. So that is class A. Then there is class B, which is at the bottom, so almost zero biased, and class AB in between these two, and class C, it goes with negative bias. So this PIC doesn't has it, it goes with this one. So that is power amplifiers classification based upon the load line. So load line means we see where is the quotient point or the operating point in the load line. What is operating point? See, this point indicates a certain amount of voltage, VCE voltage, and certain amount of IC collector current. So biasing, it is the process of giving certain voltage and current to the transistor. What voltage and current you give it to it makes the transistor to function as an amplifier or a switch. Even in that, what kind of amplifier அப்படிங்கிறது தான் இங்க more focused. So there are many types: class A, class B, class AB, class C. Class D is digital amplifier. Will not be seeing it. Any of see, look here. Class A amplifier, the operating point is in the middle. So full half cycle, you get it at the output. Class B, you get only one half of the cycle at the output. And class AB, you get a compromised response. Class C, at the output, you get less than one half cycle, less than 180. So this works for 360 degree. The output is full half cycle. This is less than 360 and greater than 180, class AB. And class B is 180 degree. You get only one half cycle. And class C is you get less than one half cycle. That is less than 180 degree. So any of see class A amplifier, whatever is the input signal you see here, you'll get it at the output. So the fidelity is very high. So for all audio applications, this class A power amplifier is used. So if it is theory, we can go in detail. This is laboratory. So I have briefed it to the most extent that is possible, right? So let's move on. So this is the circuit diagram for today. Seems to be more resemble like the previous one. Yes. So instead of a BC547, I have replaced SL100. Rest everything is as similar to the previous experiment, common emitter amplifier. So that's why I've skipped 5th and 6th experiment as per the syllabus and have come to 7th experiment and kept it as 5th experiment for the day. Right? So the same 22 kilo ohms, 4.7 kilo ohms, 1.7 kilo ohms, 330 ohms, everything is the same except the transistor. So this transistor has a very good voltage and current gain. So means the beta is more. So that's why we go for SL100, this kind of metallic transistor. So anyway, so that's the circuit diagram. See, pin diagram is more clear, right? So the same thing is what's shown here. The same kind of cutting is here, you see. Right. So from this cutting, if you go with the clockwise, it is EBC. So if it is a plastic package, we'll go with CBE, Coimbatore short form, collector base emitter. Right. Here it is the reverse, emitter base collector. So first one is emitter base collector. Emitter base collector. So that's the pin diagram, SL100 pin diagram. There is also another equivalent which is CK100. It is also the same. So the procedure is very familiar. You'll vary the frequency. You'll first set the input voltage to be 2, like common emitter amplifier, right? Then you'll try to vary the frequency and see the output voltage, right? You'll plot, tabulate the reading, and then there is only one difference here. You'll try to calculate the efficiency of the amplifier. Previous experiment, you'll try to calculate the gain. Then you'll try to plot it. Then you'll see the bandwidth. Here, the agenda is not finding the bandwidth. The agenda is finding the efficiency of this class A amplifier. Got it? We'll move on. So this is the tabulation, right? So the input voltage is fixed. The output voltage is what we are going to find out. Means we are going to tabulate. We are going to vary the frequency and note down the output voltage, because the output voltage is going to vary along with the frequency. That's why this experiment is called as frequency response. How does this amplifier respond to the frequency? Got that? So agenda is to find the efficiency. So normally the efficiency of class A amplifier theoretically is 25% or less than that. So today we'll see whether we are getting the 25% or less than that. So the 25% efficiency is very, very low. So to improve it, we go for transformer coupled class A amplifier, where the efficiency is 50%. That's the highest efficiency that can be reached through class A amplifier. If you want more efficiency and need a compromise in voltage waveforms, you can go with class AB or class B or class C or whatever. So class A can maximum, it can reach only 50% of efficiency, right? So this is what the thing we are going to do, we are going to change the frequency and note on the output voltage. Finally, we are going to calculate the efficiency. That's it, right? So it's time to go and to do it and to study whether it comes as if I told, right? Are you ready? So let's go and do the experiment. Let's see how it works. So here is the setup. So what you see here is the function generator. So that will generate the signal. So as usual, we have an RPS, regulated power supply, to give VCC, and then we have a CRO to view the signal. So the construction is here. So we have used an SL100. So instead of a BC547. So here is the collector resistor, right? And here is the base resistor R1 and base resistor R2, and this is emitter resistor. So from base, I've taken the output here, and from from the input, and from collector, the output is going. Look here, right? So this is the construction. So the VCC is given through the RPS, plus and minus goes here. And from function generator, the probe here runs to the base, and from the collector, it goes to the CRO. So input, I have kept it as 2 volt. So as usual, I have kept it as 2 volt. You can note it down here. So all that we are going to do is we are going to vary the input frequency and now run the output voltage, right? So for example, currently I have kept around 291 hertz. We don't want that. We'll try to keep 10 kilohertz. Increasing, so it went on to 28. No. Slowly. Yeah, 9.910. It's a 10 kilohertz. It should, as per the reading, it should come, the output voltage should be 4 volt. Let's go to the CRO. You can see that. You see how many boxes is covered. 1, 2, 3, and 4 into volt per division is 1 volt per division. So that is nothing but it's 4 volt. So that's how we tend to keep. For example, now I'll try to show you another reading, 100 kilohertz. Right. Let's move on to 100 kilohertz. Yeah, it's around 100 kilohertz. Yes. Yeah. Now also you can see is 1, 2, 3, 4 boxes, vertical boxes into volt per division is 1. So it is 4 volt. So that's how we need to take the reading. So the readings is easy. So now the way how to calculate the efficiency. So efficiency is output power divided by the input power that is being consumed. The output power is AC power and the input power is a DC power, right? So AC output power is nothing but there are 2 formulas for power. So one is V square by R and the other one is I square RL, right? So we are using the first one. V square is nothing but here output. So V naught square divided by RL. So for instance, we have taken this constant 4 volt. So mid-band output or mid-band frequencies amplitude. So 4 square is 16 divided by RL is 4 kilo ohms. Load resistance is 4 kilo ohms. So that's what we have done. So you get around 3.4 milliwatt, right? And with the DC input power, so it is not the power of this input AC signal, it is the power consumed. So the power consumed is from VCC. So that is nothing but VCC square divided by RI. So VCC, we know it's 12 volt. RI is nothing but it is R1 in parallel with R2. So R1 is 22 kilo ohms and R2 is 4.7 kilo ohms. So the input equivalent resistance is 3.8 kilo ohms. So that's how we get 3.8 kilo ohms. When you put the ratio, gives around 37.8 milliwatt. So the efficiency is output power 3.4 milliwatt from here and input power is 37.8 milliwatt. So the efficiency is around 8.999%. So in theory, they would say that
The efficiency is around 25% for Class A amplifier, whereas practically it comes around 8.99. So that's the thing. So similarly, for you, all the thing you need to do is you need to change V naught and find out what is the efficiency. See, I have calculated here. So note on these readings. You can pass it and you can note it down. So for 3.8, it comes around 7.93. And for 4 volt, it is 8.99. And 3.4 volt, it is 6.48. And for 3 volt output, it is 5%. And for 2.6, it is 3.78. So it varies between, the maximum is only 9 volt. That is 8.99 volt. So that's the thing. So if you want to improve, you need to go for transformer coupled Class A amplifier where it becomes 50, but practically even that will not be 50. So it will be less than that. So Class A amplifier, the efficiency is very low, but the fidelity, faithful reproduction, whatever you give it at the input without changing the shape, you get it at the output. You get high fidelity. So that's it, right? So hope you got it. You can, if there is any doubt, you can contact me or you can see the videos once again before contacting me. And that's all for today. So tomorrow, see you all with another interesting title. Hope I made it interesting, right? So see you all with another experiment. Stay safe.